Okay, good morning. Okay, let's finish this finish the equation for planes in 3D space, and then we'll get on to the new topic, which is the line equations in 3D space. So let's do a quick review. First of all, several of you asked about the assignments posting. I was just testing using Canvas, so somehow, I guess whenever I publish anything, you will receive a notice. But I delayed that, so I will upload the assignment probably today or tomorrow. Okay, so no worry. So let's do a quick review on plane equations in 3D space. So in previous lecture we learned about plane equations. In order to find the plane equation, we need two information. So we need a point P with the coordinates x1, y1, z1. We also need a normal vector to the plane. So those are two important information to construct plane equation. Once you have these two information, then you can write down the plane equation. If the normal vector is a, b, c, then the plane equation is basically a times x minus x1 plus b times y minus y1 c times z minus z1 equal to 0. Okay, so these two information, this is basically is what you need to find in order to construct a plane equation. If they're not given directly, then you're going to have to somehow find it. But usually a point on the plane is fairly easy to obtain. It's this vector here. If this vector may not be directly given to you, then you have to somehow indirectly derive using some of the vector operations. The dot product, cross product depends on the question. Okay, and this equation can be further derived or simplified into a simpler format, which is ax plus by plus cz equal to d. Okay. So the d here essentially is all the constant terms, and then you lump all the constant terms into the right side, and that's your capital D there. And as mentioned, when you solving a question, sometimes the question is find a plane equation, and sometimes the question is you're given a plane equation and you are required to solve for some other information. Now, if that's the situation, as I mentioned, if you're given the plane equation, then the first step you can do before you do anything else, and you should be able to write down the normal vector n, which is a, b, c, and here the coefficients. Okay, so that's the first step that you can do. So basically, you can summarize yourself given equation, then I can reverse getting this a, b, c, right? And the other equation you can get, you can also derive for points, right, on the plane. And we exercised this in the previous lecture. If I have a plane equation, then how do I get a point on the equation? And there are infinite number of points in equations. This is completely up to you, right? You can use a simpler way of setting x, y to be 0, solve for the z. Or you can set a y, z to be 0, solve for the x. So that either way is fine, right? Or you can go even further, just substitute x over 1, y equal to 1, and what's z, right? So there are infinite number of ways here. So point on the plane, right, equal to what? That's, you need to be able to obtain a point, arbitrary point on the plane, because sometimes you need that information to construct an additional vector or something, right? Okay. So that's plane equation. Once you have this information, you will be able to solve questions. Okay. So let's take a look at an example here, and then we can do a little bit summary in here. I'll give you two planes. So here are two planes and here. We want to find the angle between the two planes. So the question kind of says quite directly, if you're given two planes and are required to find an angle between the two planes, then it absolutely means what? Means the two planes, they're not parallel, right? If they're parallel, then there's no angle, okay, or zero. So the two planes must intersect each other. Okay? Yeah. But actually, that does bring the question here. If I give you two planes, okay, what would be the quickest way actually to determine what kind of relationship between these two planes? Right? So let's think about it. Right? If I give you two planes, arbitrary two planes, what will be the quickest way to determine what kind of relationships between these two, geometric relationship between the two planes in 3D space? Right. So for example, let's say if I give a plane, here's a plane A1x plus B1y plus C1z equal to D1. Another one, A2x plus B2y plus C2z equal to D2. So here are two planes, right? General two-plane equations. So think about it. Okay. What would be the quickest way to determine whether the two planes are parallel or not? Yes?
Normal vectors.
That's right. Yeah. If you see that normal vectors for the two planes are the same, well, I still have to be a little careful here. Not the normal vectors the same. Actually, what are the same? Directions the same, right? So, for example, right, if I give you a plane here, let's see, here's a 2x plus 3y plus 6z equal to, I don't know, that's 15. Another one has 6z, 9y, 18z equal to 5, for example, right? Yeah. So if you look at these two planes and here, the normal vector for this one is 2, 3, 6, and the normal vector for this one is 6, 9, 18. Okay. Yeah. So they appear to be different, right? They appear to be different. But when you look at it carefully a little bit more here, the second one is actually a multiple of the first one. Okay? Multiple of the first one. So when a vector is a multiple another vector, basically means the two vectors actually pointing to the same direction. Okay? Well, it could be a different direction, right? It could be a 180-degree direction. Yeah. But in this case, it's fine because when you have a plane, the normal vector, we don't restrict which direction it's pointing to, right? As long as a normal vector. Okay. So in this particular case, basically means the two planes, right? They're parallel. But I guess parallel is a very general case, right? Very general case. What's the most special case then? Perpendicular, but what's the most special case for two planes? Let's say they're parallel. Beside the parallel, and then the two planes could also be what? Coincident, right? So if the two planes are coincident, then what's the other condition we had to satisfy? We find, let's say we find two parallel vectors. That we find the two normal vectors are parallel to each other now. And what should be the next information we look for? Yes?
A coordinate should lie on both planes.
A coordinate should be on both planes. Is that what you're saying? Yes. But what's the... Exactly, yes. The constant d1, d2. You look at these two here, right? If d1 equal to d2, okay, if d1, well, actually not necessary d1 equal to d2. If in this case here, if n2 is a multiple of n1, 3 times that, right? If actually, let's say, if I do this, okay, if this is 15, if this is 5, okay, right? Yeah. If I put a 15 here, 5 at here, as you look at this, so they're not the same, but 15 is 3 multiple of the 5 here, which is just like this one. So basically means the two planes are actually the same plane, right? The same plane. Okay. So that's how you can quickly determine, right? Yes.
What if the planes are separated by distance and they're both parallel?
Yes. So basically, this is the case study here. You know what? Let's make it a little summary here. Okay. So case 1. Okay. If n2 parallel to n1, so if n2 parallel to n1, in other words, as we just summarized, n2 is a multiple of n1, right? Multiple of n1. Multiple not necessarily always is an integer of that. It could be even a fraction of that, right? You know, 1/3 or 1/4. So as long as a multiple of that. Okay. And d2 is not a multiple of d1. Okay, it's not a multiple of d1. Then in this case, the two plane, we call that parallel. Okay, call the parallel here. Is that clear? Yeah. And then the second case, okay, is the other special case now is if n2 equal to a multiple of n1 and also this d2 is same as multiple of the d1, then you get the same plane basically. Okay. Now coming back to case 1, actually, sorry, I should answer the question. If the two planes are parallel, basically means there will be a distance between the two planes, right? The two planes will be separated by a distance. Okay. This is actually an interesting part, and I actually want you to think about it for now. Given two planes, right? Given two planes that are here, what will be if this is a case like this? Okay. There will be a distance between the two planes, shorter distance for sure. Okay. So what would be the shorter distance, and how would you calculate the shorter distance? And that's a very typical question testing the planes, okay, in the area of planes. So that's in this case here. If you have two parallel planes separated by a certain distance, how do I calculate that shortest distance? Okay, yeah. So keep not the question mark at it here, right? Yeah. I think one of Simon's question probably will be just like that. Okay. So that's case 1 and case 2. Of course, last case, another case is right if n2, okay, is not a multiple, okay, or n2 not parallel to n1, okay, not parallel. So that basically means the two planes must intersect each other, right? They must intersect each other. So that's the three basically cases separating the geometrical relationship between two planes here. Okay? And this is the kind of question in this one here. Let's take a look at coming back to this question here. That's asking for the angle between the two planes. And because if I look at the coefficients, right? If I look at the coefficients, they have no multiple relationships. Okay? So they must be intersecting each other. Okay? So let's look at this particular question. How do I find the angle between the two planes at here? So for this one, I write down normal vector first, right? As I said, irrespective of anything before we solve for anything, let's write down the normal vector for the first plane, which is the 3, -6, -2, and the second normal vector, which is 2, 1, -2. So write down the two normal vectors. And it always helps you if you can roughly sketch and illustrate to this question, right, to help you basically understand or solve the question here. So let's say I'll do a very rough sketch at here. So I have two planes. Okay, so I've got two planes at here. And when you have two planes intersecting each other, as we learned, inevitably you get a line, right, intersected by the two planes. Okay. So that's two planes intersecting each other. And then we got our two normal vectors. So I guess I can draw the two normal vectors just for illustration. Okay. So they're not necessarily a precise drawing because really we don't have a computer, so it's hard to see this is the actual direction that the vector is pointing to. But still, right? It's an idea, right? It's a rough sketch. And now you're looking for is what? It's basically looking for this angle, right, between these two planes that are here. Okay. So essentially, how do we translate that question to the given conditions to an easier way of calculating it here? Okay. So I'm not going to be able to find the angle between the two lines that are here, right? Because I don't really know what the lines here is. So then all I have is the information for the two vectors here. Then, as you can see here, in order to find the angle theta, the alternative is what? You can move this n1, n2, and to start the same point. And that angle between these two vectors is basically the same as the angle between the two planes that are here. Okay. So that makes things much easier. Okay, much easier because we have different ways of finding angle between two vectors. And the easy way to find the angle between two vectors is using the formula for which one? Dot product. Okay. So cosine theta equal to n1 dot n2, and then divided by their lengths, magnitude. I got n1, n2 at here. The dot product itself is very simple to calculate. So the top one here is 3 times 2, which is 6. Negative 6 times 1, negative 6. Negative 2 times negative 2 is 4. That's the results of the dot product. And then divided by the lengths. The lengths that are here, the bottom here is square root of 9 plus 36 plus 4. Here is 2 plus 4 plus 4 plus 1. Okay. So the top here is 4. Bottom here is 9 plus 1349, so which is 7. 4 plus 4 is 9, which is 3. 4 over 21. Okay. Cosine theta equal to 4 over 21, then you can calculate the arc cosine, then you get your theta angle, which is approximately 1.38 reading if you use your calculator. Okay. Yeah. So that's another variety of the equations in the area of the planes. Okay. So as you can see so far, as we exercise, it's all about basically dot product, or we haven't come up to the cross product yet, right? Yeah. So, any questions so far? Okay. Yeah. Yes.
On case 3,
Yeah.
it says if n2 does not equal k and 1,
Mm-hmm.
then that leads to n2 not parallel. Why is it or?
So you mean y from here to here?
Yeah, like why is or?
Oh, I see. Or basically means, in my words, is,
Why leads to another?
well, what I'm saying is these two are equivalent in here. Yeah. So if they're not multiple each other, then they must be not parallel to each other. Yeah. Good. Okay, so let me do a quick summary here. We'll actually come back to plane equations once we finish the line equations. A lot of time we mix the line equations and the plane equation together in the typical type of question here. Okay. But let's do a little summary here. Let's think about what type of a question, right? Let's think about just what type of questions that could possibly arise in terms of the planes. One of my favorite type of question that I wanted to test you is to obtain a distance. So you will see a lot of questions asking what will be the distance from point to a plane, and that's the kind of question we exercised in previous lecture, that example. Right? What would be a distance from a point, the shorter distance, right? I should say the shorter distance from a point to a plane. I presented one approach in the lecture notes. There's another approach. You can take a look at it. Okay. Okay, so this is one here. And when we learn the line equations, we'll have a similar question. What will be the distance between a point and a line? And I guess another question that is, I raise it here like this, right? So, what will be a distance between two planes? I'm not going to give you a solution for now. Okay, this is somewhere I want you to think about it. Okay, if you can't think of a solution, you feel free to come here and ask me. But there will be some questions that you can exercise. Okay. What about the kind of question what's the angle between two planes? So out of this question here, more or less like a given equation for the planes, and then you derive for some other information, right? Yeah. Now, of course, there's another category of a question. Basically, is purely asking to find plane equations. Okay. So, which means you will be given some kind of conditions here. For example, very simply, you probably be given a point and a normal vector. Okay. So if you're given a point and normal vector, so that's things already solved, right? All you need to do is substitute in the formula, and you get your plane equation, basically. Okay? Yeah. However, sometimes you probably will be given a point instead of giving directly the information. You'll be given a point and another plane, another parallel plane. Okay? Yeah. So just a little bit twist. So you think about what this is. So this is a plane. Here's a point, right? Here's a plane 1. Okay. Here's a point. So this point is given. This point P is given. And then you have another plane 2, which is also given here. So this is a given, and P is given. So this is what I mean by given conditions, right? So here is the one that you're trying to obtain. What's the plane equation? Okay. Yeah. Yes.
What if the question asks there's two planes intersecting at an angle,
Mm.
and then it's asking for the equation of one plane?
Ah, that's tricky. Yeah, you can still do it. Yeah, you can still do it. All you still need to do is still try to find a normal vector basically for that plane, right? Yeah. Well, I'll put it here, right? Let's think about it. So put this. Actually, that's not in my list. That's a good one. So what yours here is given two intersecting planes, right? Yeah, given two intersecting planes, and given the angle, okay, right? And you also should be given the equation for another plane, right? Okay, and given the equation for one plane. Okay, so the question is, what's the equation for the other plane? Yeah, well, that's a really tricky one actually. Think about it. Okay. Okay, good. Okay. I'll be honest with you, it's not in my list. Yeah. So, me, no idea for now. So, I do have some idea, but I want you to think about it first. Okay, so I'll list my easy ones. How about that? Given 3 points on the plane. Okay. So you have 3 points given and asking for a plane passing through those 3 points, right? That's basically give you a unique plane. Okay. How do you get that plane equation? Okay. A few minutes here to think about it, right? So you have 1, 2, 3 points. What will be the plane equation passing through these 3 points? Anybody, any idea? Just general thoughts? Yes. Excellent. Yeah. So pick a point, right? You already have a point on the plane now, and all you need is a normal vector, and that will be the cross product. The results cross product. Okay. Good. So that's for this one here. It's not too bad, right? And this next one here we probably cannot solve for now, but once we learn line equation, we'll be able to do that. So given a point on the plane and a line, okay, to which the plane is perpendicular to. Okay, so what this means basically here is this is the plane you're looking for. You got a point on the plane at here, which is given point P, example, right? And now you also have a line at here given. So this line L, this is also given, and this line L is perpendicular to this plane we're looking for. And what will be the plane equation? Okay, yeah. And once we learn the line equation, then actually you will be able to solve that very easily. However, okay, always bear in mind, in order to construct plane equation, you only need 2 information, right? One is a point on the plane, the other is what? A normal vector. Okay, so that's all you need to construct a plane equation. So all we need is 2 information. So how do we find that 2 information, right? That's up to the specific question. then the last one here is give you a point P and a line, okay, that the plane goes through. Okay. So giving a point P and the line that the plane goes through. In this case here, we're going to make sure that the point is not on the line here, okay? And the point P is not on the line. Okay, not on the line. Otherwise, we won't be able to find this plane equation. So here's the illustration. This is the plane we're looking for. We're given a point P, and we're given a line L that the plane goes through. Then what will be this plane equation? Okay, the plane equation. That's the type of question over here. Yes?
The point would be of the intersection of the plane and the line.
But I said the point is not on the line. So because the line is in the plane. In the plane basically means every point on the line is also a point on this plane. Can you visualize that? Yeah. So that's the type of the question for this part. Yeah? Because geometrically, when you have a line and a point P, that uniquely determine a plane that goes through both. Yes.
If you had two intersecting planes, and equations for those,
yeah,
and they're also given 2 points on each of those planes,
okay,
could you find the distance between those points?
Yes, you can. Yeah. I mean, as a matter of fact, once you have the information of the 2 points, then and then it's become very easy to calculate the distance, right? Are you looking for the distance between 2 points or the angles between 2 planes?
So like a point on each different plane.
Like here, let's see. Like a point here and a point here.
Yeah.
And here's P1, let's say P2, right? Yeah. And what would be the distance between these two? Is that your question here?
Yeah.
Yeah. Okay. So this one actually, it's pretty straightforward, because let's say this is basically boils down to the basic equation for distance between 2 points now. P1, x1, y1, z1. Okay.
I suppose it's just 2 points in space, planes are kind of relative.
That's right. That's right. Yeah. But of course, you may need to find the 2 points, right, based on the given 2 plane equations. Okay. Then the distance is basically just, that's right. Right, the vector, the norm. y2 minus y1. Okay. Good? Okay. I think that those categories here, okay, pretty much covers all the possible type of questions, okay, that relate to planes. And once we finish the lines, and there will be some mixture between the planes and the lines. Okay. Yeah. So some of the questions, you can think in your head, just think of a way of, this is always helpful. You don't have to necessarily have a detailed numbers for a certain question. Even a general question, you can still think about how to solve it, right? Okay. Okay. Any questions so far? Okay, let's move on to the line equation now. Let's look at line equation now. So line equation in 3D space. You, in the first year, as I mentioned, what we typically dealt with is our planar case. Okay, so line equation so far, what you have seen is y equal to kx plus b. Okay, so slope, intersection, right? That's planar line equation. But in 3D space, unfortunately, you cannot have a single equation like this to describe a line. As a matter of fact, in 3D space, okay, line is a special case of what we so-called curve, right? So if you draw a curve in 3D space, okay, that's a curve or trajectory, right? And line is basically a special case of that. So the question here is, how do we describe this trajectory, or how do we describe this curve? Okay? So we start with the line. Later we actually will evolve to more general case, which is what we call a curve in 3D space. Okay? If I get back to this question a little bit here, we just finished this question here. If you look at this question here, we look at the angle between the two planes, and when I draw the illustration, I actually draw the line intersected by the two planes here, right? Yeah. So mathematically, you can already think of a way of describing a line. So okay, so two intersection plane must yield a line. So that's one way to describe a line equation in 3D space, right? I'll give you two plane equations. The intersection two plane equations give you the line equation. Okay, that's one way of describing certain things, right? As a matter of fact, that is one way. That's actually, I'll show you later, but not today. Given two equations, how we can obtain what we so-called the parametric equation out of the two plane equations. Okay, yeah. Now, however, okay, as you can clearly think, it doesn't really, give you a really good picture of a line when you're just being given two plane equations, right? What does that mean? You're giving me two plane equations. How can I visualize a line equation? Okay, that doesn't work very well. So I really need a different way of describing lines in 3D space. So let's think about basically a different perspective now. Okay, if this is a line in 3D space, I'm going to think of this line as if it's a trajectory. So let's say I have a point, which is point P at here. I'm going to think of the point P as a moving point. It's going to move from here to here along the line L. So that's basically what we call trajectory, right? If P is a moving point, then the coordinates for the P, which is x, y, z. Okay, so I purposely left a little bit of space at it here. Okay, so the trajectory, which is where the P is tracking along, and then the coordinates for the point P, x, y, z must be a time-changing quantity, right? Must be a time-changing quantity. Sometimes z 1, 2, 3, and then the next time is z 2, 4, 5, right? Yeah, and in other words, each one of the coordinates must be what? The time function. That make sense? Okay. So I'm kind of basically describing the trajectory of point P. But then the trajectory of point P in this particular case is a line. So then if I look at the coordinates here, then I basically would wonder, okay, so what would be an expression for each one of the coordinates, right? What would be the expression for each one of the coordinates? If I can find a appropriate expression at here, and then put them together as I change the t, the x, y, z will all change at the same time, and they happen to change along this line L. Essentially, the three expressions in here together will describe what? The line equation, right? Line equation. So that's a different way of thinking at it here. Okay. I use three functions, basically three functions, 1, 2, 3, to describe one trajectory or one line. And the three functions here, and actually they have a name. Basically, we call the parametric equation. Okay, parametric equation. Parametric equation is, you look at the wording, parameter. the t basically is the parameter right here. It's an equation, it's 3 equations, technically speaking, and you put them together, it's a set of equations. And all of the equations are a function of this parameter t. Okay, that's called the parametric equation. You see the difference now? Because in the plane equations, you only have one single equation, right? ax plus by plus cz equal to d. That describes plane. But now in this line equation, or later we call the curve equation, we're actually using 3 equations that are here to describe a single thing, which is line. Okay? Yeah, so that's a difference, right? That's a difference. Okay. Now, the question, of course, is how do I derive the expression for x of t, y of t, z of the t then, right? Which describe the line. So let's look at 2 different ways of deriving it here. I'll relate the derivation to a little more specific example right here. Okay. Yeah. So here is what I'll do it here. I'll give you 2 methods. Yeah. So let's try to find the line equation, okay, given 2 points. Okay. The line going through. It's quite easy to understand. 2 points uniquely determine a line. Right? You cannot have a second line, a third line that goes through the same 2 points. Okay, different lines. So here's the illustration. So here's Q0. Here's Q1. That's the 2 points. The line goes through it here. I'll use a little more specific numbers in here for illustration. Let's say, for example, the Q0 has a coordinates -1, 2, 2, and Q1 has a coordinate 1, 3, -1. Okay. They're not vector, okay? They're coordinates. So I have the coordinates of the 2 points. Okay. And I wanted to derive the line equation that passing through these 2 points. I'll use a little bit of physics to illustrate the derivation here. Okay? Let's just suppose I have another point Q on this line, and this is a moving point. And so this Q, let's just suppose starting at a Q0 and then moving along the line to Q1, right? Yeah. This is the point here, so a point Q. Now because the Q is a moving point, then its coordinates, okay, will not be a constant, will be a time function. So each coordinates will be a time function at here. And this point is moving along the line at a constant speed. So let's make it simple, at a constant velocity. So I used the word velocity instead of speed because velocity is a vector concept. Okay? So basically means your Q point is moving in this direction here, okay? In this direction. And more precisely, let's say at t equal to 0. Okay, initially this Q is at Q0. When t is after a certain amount of time, for example, I don't know how much of a time it passes. Let's say after a certain amount of time, and the Q is at this Q1. So it really depends on the velocity, the speed it's traveling, and that determines how much time it takes from Q0 to Q1. So that's the idea. At any other time, So Q, which is a function of t, is at its current location. At any other time, it's here or here or any other location. Okay? Yeah. So that I kind of formulated this question into a little bit of physics, right, problem in here now, right? Now let's use all of the assumption in here, and let's try to derive an equation that describes the motion of this point Q. Okay. Now if you recall, velocity equal to what? Displacement over time. Okay, physics. Displacement over time give you the velocity. So let's take a look at the current description here. I said it's a constant velocity, so it really doesn't matter where, it's always the same velocity. Then I'll pick a vector now. So I'm going to pick a vector from Q0 to Q. Okay, that's one vector, Q0 to Q. And I'll also pick another vector from Q0 to Q1. Okay, so two vectors. I've created two vectors, okay, based on the two given conditions. Now then, I'll use this simple equation here, velocity equal to displacement over time. If I use Q0 Q, that's displacement, divided by the time, okay, divided by the time. Now if you look at from Q0 to Q, how much time does it take according to the description? T, right? Arbitrary, that's our general T here. That's our general T here. Right? That's how much time it takes to travel from Q0 to Q. And that gives you the velocity, right? Now if I use Q0 Q1 as the displacement, as we describe it here, it takes how much? Capital T, right? The capital T is the much time to travel from Q0 to Q. So there we go, right? These two should be the same velocity. And we created a simple equation, right, based on the description. So now time to plug in all the known conditions now. Okay, so let's plug in all the known conditions here. What would be the and then before I plug in the known condition, I'm going to multiply the small t to the right side at here. All right, so that gives me Q0 Q equal to Q0 Q1 over capital T times small t. Okay, now I'm going to plug in all the known condition values, okay, into this equation. So first of all, Q0 Q is the coordinates of Q minus the coordinates of Q0. Okay. Actually, by the way, the other day was student asked question, realized I should emphasize this. When you're given 2 points and you create a vector between the 2 points, then it's always the coordinate is the end point minus the initial points. Okay? Yeah. The reason I want to emphasize is because actually every year there are always some students making this mistake. Okay, using starting point minus the end point. Okay. Not much different, just a negative sign difference, isn't it? Right? But it messes up the whole rest of the calculation always. So that's a dangerous mistake. So Q0 Q, and what will be my Q coordinates? It's x of t, okay, minus the coordinates of Q. The coordinates Q is -1, so -1 plus become a +1, and then y of t minus 2, and z of t minus 2. That's Q0 Q. Okay, and then this equal to the other side, Q0 Q1. So Q0 Q1 is the Q1 coordinates minus the Q1 coordinate minus Q0 coordinate. So that's -1 minus -1. So let me write down as much as possible at this stage. 3 minus 2 negative 1 minus 2. And divided by capital T times small t. So far so good? Okay. Now I also want to emphasize another very obvious mistake some of you could make. It's this negative, okay, become positive. Okay. And I've seen so many times when students do this, become still a negative. Okay. You make a mistake at this stage, then the rest of the calculation go all wrong, right? Yeah, that's something that you have to be very careful. The top one here is 2, 1, negative 3. Okay. All right, so now you actually, if you look carefully here, you already probably realize, look, I can actually obtain 3 equations already, isn't it, right? Because those are vectors on the left, vectors on the right. And when you have the 2 vectors equal to each other, basically means the components of the vectors are the same. Then this component, x component here, is the same as this x component. The y component the same as y component, the z component same as z component. So I can literally separate this into 3 equations now. So the first one is 2 over t times t, and then that's 3 equations. I'm going to simplify this equation a little bit to the standard form, because remember we're looking for is the parametric equation. It's an equation, 3 equations, right, describing x of t, y of t, z of t. So I'm going to write everything, okay, into the right side there. Now this is basically the final equation we're looking for in this example. Okay. And this is the line equation. And this is what we call the parametric equation for the line. Right? So different description. 3 equations, parametric equation, or line equation. Now they're all the same meaning at here. Okay. Is that good? Okay. So we don't stop here, okay? And now is the time actually to start to look for patterns, looking for, the connections that are here, okay? Looking for connections. So let's. I still have because here I still have what? I still have a capital T, okay, in the equation and here. So I didn't give a number to the capital T, right? Didn't give a number to the capital T here. So let's try a few numbers here. So if my capital T is 1, in this case here, basically means it takes 1 second to travel from Q0 to Q1, right? That's the meaning of this. So if I let the capital T to be 1, then this line equation becomes what? X of t equal to -1 plus 2t. And y of t equal to 2 plus t, and z of t equal to 2 minus 3t. Okay, so that's easy, right? So how about let t equal to 0.5 seconds. So physically means when t equal to 0.5 seconds, the point Q actually travels faster or slower? Faster, right? Yeah, physically. So then you get x of t equal to -1 plus 4t. y of t equal to 2 plus 2t, z of t equal to 2 minus 6t. Okay. So if I give a different numbers to the t, I get completely two different parametric equations, right? Yeah. This is basically what I want to show you at here. However, both of the parametric equation describes what? The same line equation. Okay? They look different, but they all describe the same line equation. And you can imagine if I plug in another different t's, you get different, basically, equations again, right? So this is the first commons. Parametric equation for a line is not unique. It's not unique. As a matter of fact, you have infinite number of ways, right? An infinite number of equations to describe the same line, right? Infinite number of parametric equations. Because you change the t to different numbers, you get completely different, basically, parametric equations, right? Okay. And now, second of all, okay, when I derived this, I used a physical phenomena to trying to illustrate, right, the meaning here. However, what we always try to get back is the pure mathematics. So when it comes to pure mathematics for a line equation, so for example, if I just give you this, right, here's the parametric equation describing a line. That actually is just a pure mathematical equation. May not necessarily representing a physical motion of a point or something like that. You got it? Right? So there's always a difference between a pure math equation and then you use the pure math equation to describe a physical phenomena. Okay? Yeah, there's a little bit difference in it here. Right? So what I'm trying to say here is this parameter t. Okay? The parameter t not necessarily is a time quantity, okay? Not necessarily time quantity, but it's definitely a mathematical quantity, parameter t. That's what I'm trying to say here. So parameter t is not necessarily always time. Okay? It's not all necessarily always time. So don't mix together here, but it is a parameter. Okay, it is a parameter. It's a mathematical symbol, t, right? It's t here. Yes.
Why is the parametric equation for a line not unique?
You can kind of explain it here to get some idea why it's not unique. So if I think of a line as a trajectory, right? Then to describe the trajectory, so let's see, here's a line already, right? Here's a line, you draw it already. But when you describe the point Q, you can describe the point Q with all different kind of moving patterns. Moving slow or moving fast, right? Or sometimes moving actually, it could moving backward or non-linear, right? Slow and fast. But irrespective of the motion, and after it finishes the motion, it tracks out exactly the same line, right? Exactly the same line here. So that's the idea when you have a different capital T, meaning different velocity, then you get different equation. But this equation here describes is the motion. But then when you put all the points back to the 3D space, where are all the points? They are all on the same line, right? They're all on the same line there. Does that make sense? Yeah. And I'll give you an explanation after this one here. Okay, why they're not unique. Okay. But for now, and also I want you to observe a little bit here, comparing these two equations. Okay, and I want you to observe what's the common things between the two equations. Here and here, isn't it right? This is the common. What's the different things between the two equations? The coefficient here, right? That's the different things. Okay. Now, if I look at the first, the red circle here, -1, 2, 2. Okay, -1, 2, 2. What is -1, 2, 2? What is -1, 2, 2? That's your coordinate Q0, right? That's your coordinate Q0. Okay? And where is Q0? Q0 is on the line here, right? Okay? So basically, these three numbers here, it's a point on the line, a Q0 point on the line. Okay? Yeah. And then this coefficient here, this 2, 1, 3, 4, 2, 6, right? They're literally, what is it? They're from here, right? They're from here. This Q0, Q1 over capital T. If I take away this capital T, they're just, or let T, capital T equal to 1. They're basically just what? Q0, Q1 vector, right? They're just basically Q0, Q1 vector. But if I leave this capital T here, and think of this capital T as a scale, then this is just a scaled version of Q0, Q1. Can you see that, right? So these coefficients here, they're just a scale version of the Q0, Q1, which is the vector you're connecting from Q0 to Q1 here. Okay? Yeah. Now that's an observation, and you need to take a look, a second look, okay, and get a little comfortable with this one here. But I'll give you another different method. Now this second method here is a purely mathematical method. There's nothing to do with any physical phenomena or anything like that. Okay? Yeah. Suppose this is the same L we are looking for. Okay? The same L, and we have our Q0 at here. Okay. I got my Q0 point X0, Y0, Z0. Okay. Instead of giving Q0, Q1, in this case, I'll give you the Q0, and then at the same time, I'll give you another vector V, which is parallel to this L. So V is parallel to the L. And V here, let's say equal to V1, V2, V3. V1, V2, V3. Always remember vector is a free vector, so when we see the parallel, so you can literally move it around in 3 space, right? But it's always parallel between this V and L in this case here. Now I'm trying to derive the line equation. Okay, the line equation describing a point P, which is on the line L at here. So mathematically, here's what I would approach in this question now. Okay, I will create a vector between Q0 and the P. So creating a vector between Q0 and the P, which give us X minus X0, Y minus Y0, and Z minus Z0. Okay. And once you have the Q0 P vector, then the next step here is, because V is parallel to L, the vector V is parallel to L, and that naturally means the Q0 P vector must be parallel to the V, right? So if Q0 P is parallel to V, translating into mathematical expression, meaning Q naught and V must be what? A scale of each other, right? Or multiple of each other. So I'm going to put a parameter K at it here to indicate the multiple relationship between the two vectors. So I don't know how much multiple, but I can use a parameter K at it here. So in other words, this is equal to K1, V1, K2, K times V1, K times V2, and K times V3. Okay. Putting things together, here's your Q naught P. Here is this side, K times V. Equating the two together, meaning you get X minus X naught equal to K times V1. Y minus Y naught equal to K times V2. And Z minus Z naught equal to K times V3. Or putting things the same format. Here. So we end up with another set of a parametric equation, okay, with this simple relationship. Now this parametric equation, this time, right, you know, it didn't involve any physical descriptions, okay, any physics here. All it involves is just a pure parameter capital K at here. So now this time, this K, instead of a T now, right? This is my parameter, the new parameter in this case here. Okay. Now this is a purely, but can I replace the K with a T? Yes, you can. So this is basically where the parametric equation meaning. Now you can replace the K with any parameters or symbols. Okay, any symbols. It's just a parameter. And the range of this parameter, you can take it as any numbers, right? As a negative infinite to a positive infinite number set here. Okay. Now coming back to this same this parametric equation here, and I want you to do the same observation. Okay, same observation. This portion, right? X naught, Y naught, Z naught. Where is that from? That's the coordinates for the Q, right? That's coordinate of Q naught at here, which is the point on the line. So this basically, this is the point on the line at here, right? Now what about this portion at here? This portion, V1, V2, V3. This comes from the vector V, which is a parallel to the L, right? Parallel to the L. So I can conclude now. So in order to construct a line equation, okay? In order to construct a line equation, what information do I need? You need a direction for the line, but let's put it the other way. But what you actually really need is what? You really need is a vector that is parallel to the line. Okay, it can be this way, it can be the other way. Doesn't matter, right? Okay. So basically, we need a vector parallel to the line. A vector parallel to the line. And we also need a point on the line. Okay. If you can have these two pieces of information, all you need to do is plug in this here, here, here. You get your line equation basically. right? That's the conclusion. So far so good? Yeah? So now let's get back to the question why the parametric equation actually have an infinite number of solutions or not unique. So if you look at this statement, all you need is a vector parallel to the line, right? How many parallel vectors would you have for a line? Infinite. I can literally plug in a scaled version of V1, V2, V3 at this location here, as long as scaled is parallel to the same line, right? So that number basically can change. As long as this number changes, then you get a different parametric equation. Yes?
So does that include the same thing as changing the k?
The k you actually it's not up to you to change now. The k is a parameter. Okay, the k is a parameter. It's just like your plane equation x, y, z is a variables, right? It describes a point on your plane. And here your k or this t, okay, the t, it's not a constant. It's a variable now, right? That's what we call it, a parameter. And guess what? Actually, if you change the t at here, or you change the k at here, what would you end up with? You end up with a point, exactly. And where is the point? The point is on the line, right? Yeah, that's right. Yeah.
So say if we scale the vector v by 2, right?
Uh-huh.
So that's the same thing as 2k multiplied by the vector. So the 2k becomes a scale version.
You can keep the 2 at here. Let's say you have a 2 here, right? You have a 2 at here. Okay. You can keep the 2 at here. Basically, you get a different vector set it here. Now, to make it a little more, I don't know if it helps you. If I define a completely different parameter instead of a k, maybe I can define the 2k as s. So I'll get back to my original description, right? Parametric description. That make sense? Yeah. Another thing I want you to observe here. X naught, Y naught, Z naught is a point on the line, right? And we have an infinite number of points on the line. So I don't necessarily have to pick this Q naught. I maybe will pick a different point Q1 on the line here. So if I want to construct a line equation, if I plug in a different point at here, but that point is still on the line, and guess what? This parametric equation still looks different now, right? Still looks different. So that really complicated things here, but then they all explain the same thing. You have infinite number of parametric equations describing the same line, right? The same line here. You can use a different parallel vector. You can use a different point on the line. But when you plug everything into it, it looks different. But they actually all describe the same line. Yes? It's not a different line. It's still the same line, but it's a different parametric equation, right? So I'll give you. Let's go back to this one here. Let's go back to this, right? You look at this equation here. The coefficients are different, isn't it, right? The coefficients are different. They are different parametric equation, but they describe the same line or same trajectory. Yes.
So it's basically, as the application said, it's going faster or slower on that.
That's right. See, now you're trying to relate to physical phenomena, right? Description. So if I just think from pure mathematical point of view, right? Forget about any physics. I got pure mathematical expression here. Then I can draw a conclusion is these two things are describing the same line, right? Now, if you relate to physical phenomena like this one here, then the number, right? This number here actually means how fast a particle is traveling along that line. That make sense? Yeah. I actually have a question later to kind of to kind of re-explain this concept here. Right? So this is why, when you're when you're learning in a pure mathematical department, and you probably will be presented with a pure mathematical meaning, description, symbols, formula, right? But as engineering applied science, we apply that, right, to give it a completely different meaning for that equation, right? But it's still the same equation, right? Yeah. Okay, so we're a little bit behind here now, but let me maybe start with an example here, okay? Given a line equation right here, okay, and also given a point, and I wanted to calculate what is the shortest distance between this point S and this line L. So distance is always one of my favorite questions. So actually, it really reflects all different type of approaches you can solve, making use of everything that we learned, right? But before we solving for the short distance here, a very simple concept you actually wanted to verify before you do the solving it. If you're given a line L and a point S, then I would always interested is the point S on the line L or not? Okay, that's always something that you will be interested. How do you verify that? Yes.
Plug the coordinates for S into the left side of the equation.
Yes, and then?
And then solve, and if t doesn't equal the same in each equation, then it's not on the line.
Excellent. Okay, that's how you can verify whether the point S is on the line L or not. So as he mentioned, sorry, what's your name again? Luke. So you plug the S coordinates into the left side here. Solve for t for each one of the equation. Look at whether the solutions of the t are the same or not. If not the same, then S definitely is not on the line, right? So give it a try yourself, okay? Yeah. So then I can confidence that there is certainly a distance here, right? Yeah. I'm a little running out of time here, so I think I'm going to keep it as for the next lecture to go over this question here. But I'll give out assignment number 1 now, okay, for lines and planes. So if you want, you can take a look at the lecture notes to go ahead a little bit. But otherwise, I'll cover the rest of the material next Tuesday. Okay. Yeah.
You said that this equation is not unique.
Right, not unique.
Is this one unique with the capital T? Is this one unique to the line of no?
No. Well, I mean, see, this one here, right, is based on a physical description. Constant velocity, and then starting point is q naught, right, and then it takes capital T to write there, right? Now really, if I change my description, let's say starting at a different point.
Oh, so this is unique, but it's unique to this.
Exactly.
Okay.
Right? Yeah.
Thank you.
That's how we formulate this question here, right? Yeah. Good. All right.
If we're given 2 parametric equations, how can we find out if they are representing the same?
Excellent point. Excellent point. Actually, that's something I will cover. Okay. But let's think about it. Right? If I give complete 2 different parametric equations, the first thing I will do, I'll look at the parallel vectors. So come here. So let's see if I given 2 parametric equations, right? So first thing, I will look at the coefficients here, because the coefficients. Remember what is the coefficient? The coefficient is parallel vectors here, right? Yeah. So if the 2 parallel vectors are actually multiple each other, then basically means the 2 lines are actually what? Parallel. Exactly. But parallel doesn't mean they're the same line, right? Yeah. So then the next step I would do is to verify whether the two lines actually share the same coordinates, right?
Okay.
Yeah. And to do that, we actually what we have to do is we're going to have to compare the XYZ with this XYZ. So in other words, what we do is, in this case here, it's all t, right?
Yeah.
But before I do that, I'm going to have to change one of the parametric equation from t to a different parameter, s.
For a point?
Yeah, no, just for the equation.
Okay.
If I change the t to s, it doesn't change this parametric equation, right?
No,
it's just a parameter.
Yeah.
And then I'm going to let x of s equal to x of t, y of s equal to y of t, and z of s equal to z of t.
Okay.
So basically I'm trying to solve for...
You set the equations equal to each other with our...
Yeah, so see if the end of the same solution, right?
Yeah.
If the same solution, this means all the points actually share by the 2 points, two lines. See, that's actually...
But like to quick check if the vectors aren't parallel, then they're not the same line.
That's right. Yeah. The quickest way is to look at the parallel vector.
Yeah.
If they're not the same or they are not parallel, they actually see the line here in 3 space.
Yeah.
They either intersect,
Or they don't.
they don't, or they parallel,
Yeah.
or they become the same.
Yeah.
That's something actually I wanted to summarize later, right? How do we identify each one of those case studies here?
Okay.
Does that make
Thank
sense?
you. Yeah, it does.
Very good. Yeah.
Thank you.
Good thinking. Yeah.
I have a couple of questions.
Sorry.
You guys can go first.